Okay, Raksha, if you can start yours. Okay, so it's a great pleasure to have Clay Cordova from Chicago, who will tell us about neutrino masses from generalized symmetry breaking. Take it away.
All right, thanks very much. So I'm going to tell you a little bit about a paper that I wrote in November in collaboration with Sungwoo Hong, Seth Koren, and Kentaro Omori. And we'll set up a little bit of the general sort of philosophy and mathematical preliminaries before we get into the details. But just to set some motivation, since the audience here is probably quite mixed, neutrino masses are a sharp signal. Maybe this one of the sharpest we have of beyond the standard model physics. So this is the neutrino mass. We know what do we know experimentally, just to kind of set some ideas. So there are 3 flavors of neutrinos, and we know something about their mass splittings. So that's 1. Oops, that's supposed to be 2. That's another 1. And then we know these differences, and we also know something about the overall scale of all of the masses. That if you sum, this is from the CMB, that they can't be too far apart. So the overall scale of the masses is in the MeV range. In discussing neutrino masses, there are always 2 qualitative possibilities that you should keep in mind. What are they? So for generating mass, first is a so-called Majorana mass. How does this work? Well, at the level of the standard model, what you do is you write down an effective dimension 5 operator. It's the so-called Weinberg operator. What does that look like? We add to our standard model Lagrangian. It's dimension 5, so there's some cutoff scale. Then there's some Yukawa-like matrix, which I'll call Yijn for a neutrino. And then you couple the Higgs field H, or its dual H tilde, to the lepton fields capital L, which are SU2 doublets. And then, okay, the Higgs field gets an expectation value, which is of order V. And then so this interaction after that leads to a mass term that's like V squared over lambda Yij nu I nu j. So this matrix Yij that we had before becomes the neutrino mass matrix. So that's qualitative possibility 1, and qualitative possibility 2 is a Dirac mass. So here, first we add new right-handed neutrinos. There's a new fields. They're gauge neutral under the standard model gauge group. So we'll call them N. And then what do you include in Lagrangian? Well, once you have right-handed neutrinos, then the neutrinos can get a mass through a renormalizable interaction, just the rest of the fields in the standard model. So we can have something like this. And then after the same expectation value of the Higgs, we end up with a mass of this form. So kind of Dirac mass term. So those are the 2 qualitative possibilities for neutrino masses, and in general you could envision some kind of mix of them. And a challenge in general, there are a variety of challenges to getting neutrino phenomenology, but one challenge, let me say, which is the main one we'll be addressing here, is that there's a tiny coupling constant. So let's look at y nu, for instance, over y tau. So the y of some neutrino mass divided by the y of a charged lepton field. Let's make it the heaviest to make it the most obvious. Let's say the tau lepton. And this should be roughly of order 10 to the minus 11. To match on to the numbers that we know. So especially in the Dirac mass, this is a quite fine challenge, quite sharp challenge. You see, in the Majorana mass case, you might say that y doesn't make sense without knowledge of the scale lambda, and so maybe the small mass is about a high scale. But in the Dirac mass case, especially, or in the Majorana mass case, when the scale is low, then there is this tiny coupling to explain. And so that's what we want to talk about today. We want to talk about this tiny coupling and maybe a mechanism for generating it. So our work we're going to introduce a paradigm for this via generalized symmetry breaking. I'll give you also explicit models. So not just a cartoon idea, but explicit models of both kinds of mass terms. Okay, maybe in reality in the seminar I'll only present one, but in the paper there are two. So explicit models where this is generated naturally. And here, this word natural I'm using in the sense of Dirac. So I'm going to write down a model which has only order 1 numbers in it, and then some dynamics will generate this 10 to the minus 11 for me. And so what will these models be, just before setting up the details? So these models will kind of look like this. We'll have the standard model at some low scale. So I'm plotting here energy. And then we're going to add a Z prime gauge boson. So a Z prime gauge boson means a new U1 to the gauge group. I should tell you which it is. It will be for a lepton family symmetry, L mu minus L tau. At yet higher scales, we're going to embed this into a so-called non-abelian horizontal group. So probably many people in the audience are string theorists and are familiar with sort of vertical unification. This is kind of the opposite paradigm, or a 90-degree rotated paradigm, where you have non-abelian groups acting on the different flavors of the standard model. And so so this will be our kind of qualitative picture of the gauge group. We'll have in the UV some additional new non-abelian group. It will Higgs down to U1 to L mu minus L tau, which will then Higgs to the standard model. And in the end, we'll get the neutrino map from the leptonic monopole loops, or what we'll equivalently see as UV instantons. So if you like, we're going to generate neutrino masses via virtual monopole loops. Okay, so that's the kind of slogan. Now I have to tell you how to do it. But are there any questions at this level?
I have a question.
Yes.
If you're going to gauge horizontal symmetries, then probably you'd like to aim at a theory of flavor as well. So will you have anything to say about that?
Not yet, but thank you very much for the question. It is something that I'm thinking about, but I don't have anything sort of yet to say. But it's a very obvious natural suggestion. Thank you. Yeah, I mean, I view these models that we're writing down as sort of first pass. And I hope that we have more to say about them soon. More questions? Okay, so if there are no questions about this introductory part, let's set up some of the technical structure that we'll need. So for this, I'm going to review so-called non-invertible chiral symmetry. Which was introduced nearly a year ago in a couple of papers, one by myself and Kentaro Omori, and then there's a second excellent paper by Choi, Lam, and Xiao. So let's review briefly what happened there. So we're ultimately aiming towards this phenomenological problem, but we're first going to set up some formalism. So in this formalism, we're just going to consider a U1 gauge theory with a chiral symmetry with a current J mu. And okay, it's very familiar. Oops, what happened to my pen was acting up. It's very familiar that you could have a situation where the current classically looks to be fine, but then when you go and really investigate what's going on at the quantum level, you'll find an equation like this. So I'll even attempt to write the pi's. So this is f wedge f with some coefficient. And so this is the sort of quantum situation that is often the case. And here, k in z, k is an integer, which is anomaly or triangle coefficient. So the diagram that we are discussing right now is a familiar one. So we have a loop of charged chiral fermions. We have our we have try again, loop of charged fermions. We have our current coming in. Here's J, and then we have two photon dynamical gauge fields coming out. And of course, we have a formula for K that you get from this, which is the sum over all Weyl fermions of the charge under J and then the charge under A squared. So if K is not 0, then the naive charge is not conserved. So what was the naive charge? It was the integral over all of space of J0. And the problem with this naive charge, it's not really a good charge. Okay, so all of that is kind of ancient history. But there's a long-standing puzzle in this. Let me highlight the puzzle. So when you look at this equation, you might say, well, the divergence of J is 0, this equation up here. The divergence of J is non-zero. So maybe I should just forget about this J. Maybe it's not really a symmetry anymore. But of course, physicists have long known, we've long known that that's not a good point of view. In particular, on R4, with only local operator insertions, then one has the following integral formula, which is that the integral d4x epsilon mu nu rho sigma f mu nu f rho sigma, this is just 0. So the selection rules still hold. At least in this limited situation where we have only we have kind of restricted ourselves to standard R4, space-time, and local operator insertions. But that's actually quite a general situation that describes, for instance, all the S matrix phenomena that we might try to study in this theory. So the puzzle here, kind of question that you might try to ask is, what is the charge for this? How do I think about this kind of symmetry? The current isn't conserved, but nevertheless, there's still something good. There's still some selection rules. So let's try to make it sharp. What is the exponentiated Noether charge? Or in a modern language, the symmetry effect. Okay, well, there's a whole talk that one can give about this, but let me tell you kind of what the resolution is. Are there any questions about this puzzle? I think it is well known, but please feel free to ask the questions that you've always wanted to ask about it. No? Okay. Okay, so what is the resolution of this that was introduced in those papers? Okay, well, the resolution is that we're going to stack the naive Noether charge with a fractional Hall state. So let me write what that is, and then we can unpack it. So we're trying to introduce a finite chiral symmetry rotation. That's what the exponentiated charge would do. So here will be the place where you could think of this as some spatial slice. Let's call it D, the operator that we're trying to construct there. So this is a spatial slice where we're trying to do with a chiral rotation by 2 pi k n, 2 pi over kn. So I'm trying to do a fractional rotation by 2 pi divided by some integer. Okay, so what is supposed to live here? How am I supposed to accomplish this? Well, one part is easy. I take the naive integral of J0, and this is the integral over D, if you like. Well, maybe D is the defect, so I'll not call it D. So I take the naive integral of J0 over this locus. But this is not enough. J0 is not conserved. So what is the additional thing that you put here? You put something kind of interesting. First of all, the thing that we're going to put here is the partition function of a dynamical theory. So C here is going to be a new U1 gauge field. So what is the action for this C? Well, it will look as follows. We'll have a Chern-Simons term for C. And how will it couple to the ambient? So we have this Chern-Simons term for C, the level is N. And how will it couple to the ambient bulk gauge theory? Well, it couples through this kind of term here. So a kind of mixed Chern-Simons term, like that. So this is, we have this kind of novelty in this symmetry that we're trying to construct is that we don't just have the naked integral of the current. In fact, we know that we can't really have the naked integral of the current. That's not conserved. Instead, we have this additional coupling to degrees of freedom that live here on this spatial slice where we're doing the chiral symmetry rotation. And they couple together through this off-diagonal Chern-Simons term, which, if you know a little bit about some condensed matter physics, this is exactly the coupling in the fractional quantum Hall effect. So this is exactly how degrees of freedom couple to electromagnetism in that story. So C here is, so just to highlight some of the features, C here is a new U1 3D gauge field with the Chern-Simons term. Note that here I'm doing a chiral rotation by 2 pi over kn, and the interactions that I'm writing here, the Chern-Simons level in particular, depends on this n. So, okay, so I said this in words, but what else can we say? It couples to the bulk via this, C wedge F term. This is the F of A. Why did I introduce this? Well, the main reason, the main thing that you need to know is that this is conserved in time. Exactly, on any manifold with any operator insertions. So this is a, if you like, a topological operator. So it's a modern definition of a symmetry. And finally, it fulfills the criteria that we want, which is that it explains the selection rules that we found on R4 for local operators, because it acts on local operators as a finite chiral rotation. So a finite chiral rotation by that angle there. So in a sense, this explains why this chiral current J mu with an abelian Adler-Bell-Jaquiev anomaly generates a symmetry. Questions about these essential features? Okay. Well, you could ask, what is the price I pay for this anomaly? I mean, I seem to have just gotten something for free. And well, I didn't get something for free. The ABJ anomaly, it has some interesting consequence for these operators. It leads to an unusual symmetry composition rule. So the rule is that if I take D, that's this finite chiral rotation that I was trying to construct, and I tried to collide it with D dagger, usually that would be 1 for a unitary operator, but here it's not really 1. That's the unusual part. Instead, it's a sum over surfaces. There's some homology details that I could tell you about, but it's not very important for the story I'm telling today. It's a sum over surfaces of the following kind of operator. Integral of x of f, the field strength. This is the flux of the bulk gauge field A over the surface. So it's not one. Instead, this right-hand side of this DD dagger is a sum of magnetic flux operators and in particular, that means that it is trivial with all local operators. So local operator insertions are blind to this kind of magnetic flux sum here. So for them, D dagger is really 1. So that was an important feature because one of the things we were trying to explain was that there apparently was this chiral symmetry, even though there was an abelian ABJ anomaly. And the chiral symmetry looked just like kind of an ordinary symmetry. It looked unitary, it looked like acts by finite chiral rotations on local operators. We see it in the S matrix. So D is fulfilling all those criteria. Where will you see this sum though? You will see it, and this will be important for us in a minute. It's non-trivial when you have 't Hooft lines inserted. So a 't Hooft line, I remind you, can think as the world line of an infinitely heavy monopole. So just to jog your memory, what's a 't Hooft line? Well, here's the world line of the monopole. Let's call it M. Now, this is a picture in space-time. Linking around it is some S2. This is the space-time picture. And if instead you wanted to think in space, well, you could think there's just, in space, there's just some point charge M. And this linking two sphere is easier for our little brains to visualize. It's just this standard picture. And the 't Hooft line has the feature that the integral of F over this S2 is equal to the magnetic charge. Kind of the magnetic analog of Gauss's law. And so when you have 't Hooft lines inserted, the right-hand side will become a non-trivial operator. And this is kind of intuitive, you know, if you have, I said that divergence of J integrates to 0 on R4. But once you have enough magnetic charges inserted, you'll really see the non-trivial integral of the divergence of J over space-time. Okay, so questions about this? All old hat. Okay. Very good. So what's the lesson that we will need? So why did I introduce this? The lesson that we will need here, and this is where we're going to get some of the physics, is that a chiral symmetry with an abelian ABJ anomaly forms an algebra, kind of algebra. I'm using the term algebra a little bit loosely here, but it forms an algebra with the magnetic charge. the magnetic charge is a one-form symmetry. That's what this equation up here means, right? You can think that this equation tells us that once you have D, it doesn't make sense to not have the one-form symmetry. If you fuse the Ds, you get the one-form symmetry defects, or more precisely, they're condensates. And what are we going to get from this? Well, this presents an interesting point of view on symmetry breaking. If you want to apply symmetries in particle physics, it's mostly about thinking about how they are broken by small effects. So that's what we are going to do here. So what's the consequence? The consequence is that dynamical monopoles, that means finite mass, they will break the chiral symmetry. That's a universal consequence from this discussion. Why is that? Well, dynamical finite mass monopoles break the one-form symmetry. And that will be communicated back to this chiral symmetry through the algebra that I highlighted before. You can actually estimate the size of this effect. At least in a kind of regime where you have control. So here we have the monopole mass. Let's imagine the monopole mass is say V over G, where V is some Higgsing scale and G is coupling. So V is some scale and G is a coupling. So the monopole mass is this. There's also a cutoff when you think about we're thinking about like kind of effective monopoles in a effective U1 theory. So a theory that I'm envisioning is a U1 gauge theory, but now we have some heavy magnetic monopoles in the problem that are, and we want to understand what happens with them. So we have this coupling, we have this scale, and then we also have a cutoff of our theory, lambda, which would universally, you would think goes like V times G. So if you like, this is like the W boson mass from when you Higgs some ultraviolet non-abelian theory to generate these monopoles. And we could think that this cutoff scale determines sort of a short time scale. We'll call it delta T inverse. This is our cutoff. This is the monopole mass. And this is the cutoff of our U1 theory. And now, if you want to understand how big are the symmetry breaking effects coming from dynamical monopoles, to think about it in kind of a universal way, we'd like to use this effective U1 gauge theory that I was just discussing. And so to do that, we like to think of it in a kind of first quantized formalism. So we think about a monopole loop, a virtual monopole loop. That would be the first correction. It has an action, which is like e to the minus s, or the exponentiated action. And this will tell us the size of the first correction. So it will be like an exponential, roughly speaking, of minus the monopole mass times delta T inverse. So that's kind of the saddle value for the loop, if you like. And you can just look at these formulas and determine that this is like an exponential of minus some number that I can't determine from this very wiggly reasoning, divided by G squared. So that the scale V canceled out, but we did get 1 over G squared in the exponent. And so what we learned is that loops of monopoles will violate this chiral symmetry non-perturbatively.
Sorry, can I ask a question at this point?
Sure, of course.
So if you view this U1 as embedded in some non-abelian gauge theory,
Yeah.
Is what you're saying the statement that there are instantons in the UV, they're very suppressed? This is your monopole loop?
Yes, exactly. So that was exactly going to be the next line I wrote. Thank you for the question. So maybe I'll just write it now. So this links monopole loops with UV non-abelian instantons. So of course, this is the kind of qualitative form that you would expect from a UV instanton action. And okay, if you have from a top-down point of view, what we're going to be talking about is some interesting instanton effect that will be the leading effect violating some symmetry. From a bottom-up point of view, we can think in the effective U1 theory, it will come from loops of monopoles. We can kind of use the infrared reasoning, or we can use a UV reasoning. The infrared reasoning is sometimes more powerful in the sense that maybe you don't want to commit yourself to a particular UV completion. But when I write down a concrete model, I will indeed take the avenue that you suggested.
Okay, very good. But I have a follow-up question. Now, I would think that the mass from the instanton comes from the 't Hooft vertex, correct?
The mass from
the mass of the fermion.
It will eventually come, yes, from that. Yeah.
But if you have multi-flavor, several flavors, the 't Hooft vertex is not a mass term; it's in some higher power.
Well, this I will answer more explicitly in a minute.
Okay,
Yeah.
great.
No, I'm not. I'm going to really write down such a term. But you got to give me a little bit more time. But thanks for the anticipation. Okay, so we've set up all the kind of story that we want. So now, what will be the essential idea of the models? So we'd like to protect neutrino masses by a symmetry with an abelian ABJ anomaly. And then we'd like to embed whatever, so this is kind of our infrared story. And then to get the small mass, we're going to embed into some UV. It will turn out to be a non-abelian gauge theory in the models that I write down. So with monopoles to generate a small mass. Now, before I write down the models explicitly, it's worth emphasizing sort of what's the advantage of doing things this way. Maybe you just say, well, just start from the top down, write down these models. Why give this long song and dance? And I guess what I would like to point out is that if you start from this kind of effective field theory point of view, this U1 point of view, where you're organizing it via these generalized non-invertible symmetries or higher symmetries, then you're led to sort of a general paradigm. You kind of whenever you find such a symmetry, you always know that there might be some nice UV completion you could find where there's a violation of that symmetry by a small amount. So it gives you kind of an organizing principle to hunt for hierarchies. And that's the point of view that I'm advocating here. Okay, so without further ado, let's start writing down some models. Okay, so we'll start with a Z prime with L mu minus L tau. That's the symmetry group in the standard model that is gauged. So this is our model. And I'd like to tell you about its symmetry, of course. That's the name of this seminar. And explicitly in the discussion, I'm going to tell you about the Dirac mass case. There are models in the paper for Majorana masses as well. Okay, so in the standard model, there aren't that, we're going to have a model where we have an additional U1. There aren't that many U1 symmetries of the standard model. But lepton family differences are symmetries. So lepton number itself, U1L, is not a symmetry. It has some non-abelian ABJ-like anomalies, which really destroy it. But lepton family differences are symmetries. So we're going to gauge L mu minus L tau, and I should say that gauging L mu minus L tau, that class of models is a kind of standard. Is a phenomenologically appealing scenario or well-studied scenario for neutrino masses in particular, and perhaps other effects. So people often discuss building the texture from the pattern in neutrino masses from the pattern of Higgsing L mu minus L tau back down to the standard model. And we may discuss that a little more later. Okay, so we need to make a table with all of our little symmetries and so forth. So, okay, what will be our gauge groups that we need to discuss? So we'll have SU2L, that's the weak force. We'll have U1 hypercharge. We'll have this U1 mu minus tau. We'll ultimately have some non-abelian horizontal group SU3H. And then we'll have three other quantum numbers that I'll call L tilde, N, and L, which will just be L tilde minus N. Okay, so these are our gauge groups. What are our fields? Well, okay, there's going to be a lepton field, which comes in three varieties, Le, L mu, and L tau. And I should say, of course, I'm ignoring color here. Color will just come along for the ride, doesn't play any role. So we have this this triplet of fields here. Of course, they're a doublet of SU2L. I'll use the theorist conventions where they're where they are charged -1 under U1Y, and then their charges under U1 mu minus tau. You just read off by their subscripts. And ultimately, we'll put these in a fundamental of SU3H. These guys have, I'll tell you what these quantum numbers are in a moment, but maybe some in the audience can already guess. So that's one field. We also need E bar. Oops. Where did I go? Here I went. Excuse me. E bar, so that's E bar E, E bar mu, E bar tau. These are singlet. They have hypercharge +2. We got 0, -1, 1. They'll go into a 3 bar. -1, 0, -1. Okay. The other fermions that we'll need to know for this Dirac mass model are our friendly right-handed neutrinos. So they come in, again, 3 varieties. They're neutral under the standard model gauge group, but they're charged under U1 mu minus tau. They'll also go into a 3 bar. And then finally, I'll remind you of the quantum numbers of the Higgs, which is 2, -1, 0, 1, and then 0, 0, 0. Okay, so those are the fermions that will play a role here, and their quantum numbers. We can scroll back up to that as needed. So the gauge group in this model, just to write it more explicitly, is SU2L times U1Y, where there's also an SU3 color, and then there's a U1 mu minus tau. Color plays no role in this discussion. And then what were the these quantum numbers that I was writing at the end? So there's L tilde, which we'll define to be the standard model lepton number. So that's a lepton number that acts only on the standard model fields. It's not conserved quantum mechanically, but it looks like a good classical symmetry. It'll play a role in a minute. Then there's N, if you like, this is like the right-handed neutrino number. And then there's the true lepton number, L, which is L tilde minus N. This is the real lepton number. Okay. Now, this game that we're playing is all about various anomaly coefficients, so we'll need to know those. So let's write down what they are, and then we'll say what the consequences are. Okay, so SU2L squared, we're looking at the anomalies that are like global, gauge, gauge. So okay, now I will write down the anomaly coefficient for L tilde and L. Those are the two linearly independent things that look at least classically like they're going to be symmetries. So for L tilde, the anomaly
have one more column, which is U1, U minus tau, U1Y.
That one is 0. But yeah, like it won't play. It won't be important in this discussion. But yes, I'm not telling you about it because it's not interesting. Okay, so right. So thing we need to know are these coefficients here. This is what we need to know about these coefficients here. Okay, so let's interpret what we learn about these two classical global symmetries, L tilde, which was the standard model lepton number, and L, which is the true lepton number that takes into account the right-handed neutrinos. And the first thing we can say is that gauge interactions including, in particular, say SU2L. Okay, so this is a non-abelian ABJ anomaly. So this is going to violate L tilde and L, but it's going to preserve Z3 subgroups. So ignore for the moment this SU3H. We're thinking about a field theory that for the moment just has these gauge groups. So they preserve Z3L and Z3 L tilde. Okay. And those are very interesting symmetries from the point of view of neutrino masses. So Z3L, this forbids Majorana masses. Remember, we talked about the Weinberg operator, this kind of term like this. Or we could also, once we have the right-handed neutrinos, we might have to consider NN type masses. And these are excluded by a Z3 true lepton number, under which both N and L rotate by a third root of unity. Okay. Now there's the other one, the kind of L tilde Z3 that acts only on the standard model fields, and this forbids Dirac masses. No longer, so that's not allowed by this Z3L tilde. Now, why is this related to the first part of the talk? Well, we're supposed to notice that Z3L tilde has an abelian ABJ anomaly with this L mu minus tau abelian group. So that's this coefficient up here that I'm highlighting. And now we can say, okay, this Z3L tilde is one of these non-invertible chiral symmetries, therefore, that we constructed in the first part of the talk. And what to say about it? Well, let's just put a little more meat on it. So Z3L tilde, the symmetry defect, it supports a U1 level 3 Chern-Simons theory. So, and what that means is that a kind of monopole, a tuft line of L mu minus L tau these can excite anions on this symmetry defect whose spins are a sixth. So that's the physics of that symmetry defect in this context. Okay, so that's the U1 effective field theory that we'd like to talk about. It has these two Z3 symmetries, which for one is a standard invertible symmetry. That's the true lepton number. That forbids the Majorana mass. The other is a non-invertible symmetry, which forbids the Dirac mass. And that's the story from the point of view of this Z prime theory, where we take the standard model and we gauge L mu minus L tau, and we add right-handed neutrinos. Now we'd like to look at a higher scale. So we'd like to generate a small symmetry breaking effect. So let's look at a higher ultraviolet scale. We'll call it V sub phi. Phi will be some field that condenses. And at this scale, this U1 L mu minus L tau, we'll think of it as embedded inside a non-abelian horizontal group, SU3H. So this is, if you like, going to be my UV, this SU3H gauge group. Okay, so what will the Lagrangian be at this, the classical Lagrangian that I'll write in this SU3H gauge theory? Well, I'll just write something like Y tau, H, L, E bar. Now, if you scroll up here, we can see that L is a fundamental of SU3H and E bar is an anti-fundamental of SU3H, and H, the Higgs field H, is a singlet under SU3H, so it makes sense to write a term like HL E bar. And there's a single coupling, which we'll take to be the tau-Yukawa coupling. And this coupling, this story here, this interaction, this classically respects oops, how does that happen? Classically respects what? The Z3L times Z3L tilde symmetry that I was highlighting before. But now, because of this Higgsing, there are dynamical monopoles. These are not monopoles of electromagnetism. They are monopoles of this U1 mu minus tau gauge group. And so these dynamical monopoles mean that Z3 L tilde is broken by quantum effects. And these become calculable in this gauge theory. I should say that Z3L remains, though. So since we're in this UV gauge theory, we can understand what's going on by looking at a 't Hooft vertex. So there's an instanton, an SU3H instanton. Which generates an 't Hooft vertex. Okay, how do you figure out what kind of 't Hooft vertex is there? Well, each 3 and 3 bar of SU3 has one zero mode in the presence of a single instanton. So the 't Hooft vertex is a product over the zero modes. So it will have a term that looks like L E bar L N. That's because there's two L's because the L's are in SU2 electroweak doublet. So that's why we get 2 of those. And okay, there's a scale. So this is a Higgs instanton. So there's a cutoff scale here, which is the scale of this Higgsing B5 -2. And then there's, of course, the instanton action, which I'll write like this, -2 pi over alpha H, the coupling squared of the SU3H gauge field. Okay, so that is not a mass. So who cares? Well, we still have this classical interaction here. So we can contract with the classical interaction. We contract with the classical lepton Yukawa to get a Dirac mass. So what will that look like? That means that our Lagrangian will go like y tau, instanton action, and then our Dirac mass that we were looking for. So if you think about it in kind of like a diagram notation, we have something like this. There's some blob here. This is an SU3H instanton. And it has legs that look like this. It has an N leg and it has 2 L legs and an E bar leg. And then these can join using this classical vertex here that we wrote to H. And so this composite is generating this interaction. Okay, so that's the mechanism for generating the mass. We should try to get some more physics out of it. This was what I wrote here was valid kind of above the scale or at the scale V phi. But let's run it down. So V phi is where I remind you where SU3H was Higgsed to U1 mu minus tau. Let's run it down to the mass of the Z prime. The Z prime is the gauge boson for U1 mu minus tau. You can do that. We know the beta function because we know all the fields in our model. So you get a formula for the neutrino mass that looks like m nu is m tau times V phi over mz prime to the 4/3. And then we have this, need a new pen, exponential of minus pi over 2, this alpha mu tau of mz prime inverse. That's the formula. So why did I write this formula? Well, it's a pretty tight relationship. So there are not very many parameters to tweak in this kind of model. So if, in particular, if you're given mz prime and alpha mu tau, these are the kinds of things you might try to measure if you discovered a z prime gauge boson. So you would measure its mass and its coupling strength. And once you're given that, well, we already know the mass of the neutrino and the mass of the tau lepton. So that implies that this Higgsing scale, this UV Higgsing scale, is fixed. So the model would tell you, if you discovered a Z prime gauge boson, and this was the right model of neutrino masses, it would tell you where you should find this non-abelian horizontal group. And because of the exponential scale, it's kind of most interesting if everything is sort of low scale. So, you know, for instance, if mz prime is a TV, then if you want v phi to be between mz prime and the Planck mass, then the gauge field can't be too weakly coupled even. So you get something like this. Just to put some numbers on it. Okay, that's what I wanted to qualitatively tell you about this model. Perhaps I will write some final comments before concluding. So some last words. One thing that's kind of novel about the model that I presented to you is it's a pure Dirac model. It's a pure Dirac model where I got this scale y from some natural non-perturbative physics. So in particular, Z3L, which was killing the Majorana masses, this remains unbroken, even in the extreme UV. So that, I think, is an interesting point. It's a pure Dirac model. Of course, there is a Majorana model, which I'll comment on in a minute. Now, many of you may be wondering about the neutrino texture. Neutrinos don't just have a small mass, but they have a big matrix of mixing angles. And what I haven't told you about that at all. So is this really a reasonable story to be telling? Well, yes. You can generate this rather easily by the scalar Higgs sector. Here, I don't mean the standard Higgs field. I mean the Higgs field that's responsible, for instance, for breaking U1 mu minus tau down to nothing. After all, we don't see U1 mu minus tau right now. So that introduces a whole bevy of Higgs fields, or if you like, even just one Higgs field. And you can use the couplings to this Higgs field and some spurion analysis to generate a neutrino mass matrix of mixing angles. But importantly, because it is a Higgsing process, all the entries will be proportional to this instanton action that I wrote down. So this coupling that I wrote down will be like the seed, and every additional coupling will be proportional to that in the final mass matrix. So if you like, what I'm doing here is I'm factoring the problem of neutrinos into two parts. The neutrino mass matrix is like a chaotic matrix of order 1 numbers times an overall small number. I've given you a theory of the overall small number. And then I'm just going to append that theory onto this kind of standard neutrino phenomenology for generating the mixing angles. Okay, and then finally, what about this Majorana model? Well, for that, you have to read the paper, or at least take a look at some of the tables. So but just to give you a cartoon, it's very similar. We have a standard model. We gauge U1 mu minus tau, but now instead of in the UV having SU3H, we have a kind of interesting electroweak type pattern where we have SU2H times some U1. So this is like the electroweak coupling. But different gauge set groups here. And the U1 mu minus tau is a combination of the U1 here and the U1 and SU2H. And so that can be used to generate Majoron and neutrino masses via generalized global symmetry breaking, in much analogy with the Dirac mass case. Okay, so I guess I'll stop here and take any more questions if there are any.
Okay, great. Thanks very much for this really nice talk. Other questions? Maybe I can start off with a question. So you were saying about the texture. Essentially, you use sort of the sort of standard mechanism where you just give some scalar VEV, so some Fogart-Nielsen type mechanism, right?
Yeah, exactly.
So,
yeah.
so basically, nothing new is happening. It's just coming.
I have
this
not added
overall.
anything at all to that story at all. I'm just sort of what I'm explaining is sort of like an overall
Yeah,
small number
okay.
multiplying that matrix.
Right.
Yeah.
And in your sort of model with this Dirac mass, the MZ prime, basically, if you input these, so what are the bounds at the moment for Z primes? And if you sort of, we were saying TV, but could you make V phi that scale to be like gut scale and use maybe some kind of gut model that would perhaps spit out something naturally?
It's
like
an interesting question to do it with a gut. I mean, it would have to be a horizontal gut.
Mhm.
So, you know, string theorists are more familiar
I
with the
understand.
vertical gut, which acts generation by generation, but this will have to treat the generations differently to do the kind of thing that
Right.
we're talking about. So, you know, you can make V phi. You want MZ prime to be at a TE at the gut scale.
No, I didn't want that to be at the gut.
Or you
scale.
want V
The
phi
first
to be at the gut
question
scale.
was whether the MZ prime is actually allowed to be at TV scale.
Yeah, there are, I
Currently.
mean, maybe not exactly 1 TV, but my impression is that especially mu minus tau, because it couples to the heaviest generations,
Yeah.
is pretty weakly phenomenologically constrained. So maybe even a TeV is not yet completely ruled out.
Okay.
And V phi here can be all the way up at the Planck scale, though, you know, you start to get into a regime of stronger and stronger U1 couplings.
Mhm.
You know, this is alpha, so there's some 4 pi's in here.
Mhm.
But yeah, so so it doesn't exactly, it maybe can work. I mean, you know, the details of this formula depend on the explicit matter content.
Right.
Because it was like
Mhm.
from the beta, it was the UV part was sort of very universal, and then I had to run it. So you might imagine that, yeah, you can change the numbers a little bit by tweaking the matter content. And it's not unreasonable to think that there could be some kind of like combination horizontal vertical unification that does this. But I haven't thought about it very much yet.
Okay, any other questions?
So it is somewhat unrelated, but I wanted to ask you if you've thought about, of course, we have the Higgs mass hierarchy that we would like to understand.
It's an excellent question. You're asking if I know how to explain kind of the old school one of the older kind of real hierarchy problem, if you like, using this. No, I don't know how to do that. You know, in a sense, the concept that was introduced here from the point of view of symmetry was fairly mild. Like there was already a kind of beacon that there was a symmetry. There was a chiral symmetry, right? They're kind of, if you ask phenomenologists know that there is this kind of chiral symmetry, but maybe what I introduced is sort of a mathematical language for that, which gave it and that language pointed to a universal symmetry breaking mechanism. On the other hand, the Higgs mass operator, at least in a weakly coupled theory, where you think of that operator is really like HH dagger. So not some strong coupling Technicolor, you know, something like that. But if that operator is really HH dagger, it looks challenging because to figure a symmetry that could act non-trivially on that. Because if you have any kind of symmetry operation that acts on H, will automatically make HH dagger neutral, as far as I'm aware. So you would need some strong dynamics, I think, so that you wouldn't want to act directly on the elementary field H. But that would put you in something like the regime of Technicolor or conformal Technicolor or something like that, which is highly disfavored phenomenologically, I believe. So yeah, the upshot to your question is that I don't have a good idea about that. Of course, I would love to have an idea about that, but I don't have anything to say right now.
Okay, thanks.
Juwen.
Yes, thanks. I have a question. Thanks, Clay, for a nice talk, and thanks, Sakura. So the question might relate to earlier comment from some person. I didn't notice the name, but it's about, can you clarify again the relation between the magnetic monopole loop and the 't Hooft line, and also some instanton effects that you already mentioned, and also the calculation of 't Hooft vertices. Just summarize all this story in a coherent way. Just let me understand better. Thanks.
Sure, I will try to do that. So so a 't Hooft line is the world line of an infinitely heavy monopole.
Yes.
So that part I think you're familiar with. Now imagine if you're in this U1 gauge theory that we were just discussing with these 't Hooft lines, and you want to think about what happens if the monopoles are not infinitely massive. They have some say large finite mass, so a mass that's above the electric degrees of freedom. Well, then you can take that into account in a sort of first quantized formalism by summing over loops of monopoles. So there's a nice paper I should mention in this context that recently maybe appeared about a year ago by Gigi Fan, Matt Reese, Catherine Fraser, and John Stout, which talked about talked about like axion potentials in this context. So yeah, so you want to study in a U1 effective field theory the effective monopoles, and you can do that without writing a true monopole field in the Lagrangian. You just sum over, you just treat QFT sort of in the world line formalism, where you sum over numbers of insertions of loops of the massive particles, sort of like what we do in string theory. And okay, so that's kind of the IR point of view, and then from a UV point of view, at least in kind of favorable circumstances, that just matches on to the calculations that you would do using UV instantons. So, I mean, you have to be a little bit careful in the sense that it's not just that although I kind of sketched the order of magnitude being that it's just like a single magnetic monopole that gives you a single UV instanton. That's the right level of the order of magnitude, but it's actually like a resummed kind of monopole loop gas that's giving you a single instanton effect. So you can look at that Fan, Fraser, Reese and Stout paper to see those details. So yeah, that's sort of what I know about this.
Thanks. Thank you.
Hey. I think that was, by the way, Tin Suleiman Pass. Well, I actually don't know how to pronounce his last name, but Tin from Durham who asked that question. Okay, are there other, yes? Okay. So anyway, let's thank Clay again for this nice talk, and we'll stop the recording.